questions of the nature of the strongly interacting states in the polarized dipolar molecules. So, at the beginning I'll discuss ab initio first principle Monte Carlo results for dipoles and the lattice, and demonstrate that there is a raffining transition for single chain. I'll explain what these chains are. Then I'll consider sort of model calculations for several chains, sort of soup, spaghetti, quantum spaghetti of these chains, and discuss that such states should exist from the perspective of the customization in 1+1, and then presents model simulations in terms of J-current model in 2+1, and actually raise the question that there, in this system there could exist a quantum disordered state. So what are these dipole molecules? So let's imagine these balls represent polarized dipoles, either magnetic or electric, in z direction, and they can live along either cigars or planes, and there is no tunneling for simplicity between them. Actually, result still is valid for with tunneling, but let's presume there is no tunneling. So they're pretty much independent, but interaction between them can result in forming chain formation. So there is attraction in this direction, and repulsion in this direction by the nature of the dipole-dipole interaction. So natural expectation is that there are chains, and actually such chains were observed in classical systems, discussed by Yuri Lazarek and Mandelstam more than 20 years ago. Recently, the question about such quantum chain formation was addressed in this paper under the assumption that these chains are rigid, not flexible. So this here, I will just raise the question about the nature of the flexible chain state.
You said it might have an additional direction in that way. So in
it
that
could
case,
have.
but you'll still have chains in that case?
Yes, in 2+1 and 1+1 there are chains.
So one is this, and 1 or 2 is the other two, right?
No, 1+1 I mean time
Repulsion.
direction, imaginary time. Because it's
imaginary.
quantum problem.
So this is 2+1, right?
Well, it's if you wish, this is one-dimensional cigar, as it's shown. This is one dimension direction. You should add actually number of layers. It's another direction, right? And there will be third direction if I consider a plane instead of cigar.
But you will consider cigar.
No, cigar and plane. I present results for both.
But
When-
why
when
don't
you-
you form a sheet in that case? You still form a chain, not a sheet.
Well, it is a sheet in terms of imaginary time. And chain is
No,
formed
I mean in real,
it's
in
in
real
membrane.
space. In real space.
in real space. So, why should they form sheet? Because there is attraction, repulsion in this direction, so they cannot stick together.
Yeah, but what happens in that direction?
Of the same story.
So the Z story
polar.
one.
There is a symmetry, polar symmetry.
So it's repulsion or
Repulsion, yes, around in this direction there is a repulsion. It's
So
polarized dipoles. These are polarized dipoles.
Okay.
A related question, so the chains are just defined by ordering. If there is no rigidity, then the chains are defined just by ordering.
I'll show what the definition of the chain is. I will show you. I explicitly show what it means to have a chain.
And why did you link them like this? Because you could have, for example, break
Absolutely.
a chain
Yes.
and break a chain and
Yes,
have a piece
absolutely.
of a chain.
Absolutely. They switch, of course. They are indistinguishable particles. It's just a cartoon. It's just a cartoon.
Yeah. I want to make sure I understand what you're counting.
No, I'll show you. It's just a cartoon, a classical cartoon, and we begin with a single chain when there is no such a question. Right? Okay, so just one particle for each layer. I call it layer anyway, cigar layer. And there could be just single chain. So the Hamiltonian were used for ab initio calculations is standard one. So basically, we have jumps on the lattice. We have jumps, nearest neighbor jumps within the layer, and there is an interaction between layers. And this interaction is standard type of interaction. Okay.
So is it bosons A and A?
Bosons.
So, but isn't it model fermionizable? Doesn't it map directly on, let's say, spin model or fermion model? If you have only basically single chain hoppings, it's basically equivalent to X model.
It's probably possible to solve single chain analytically in case when you replace it by delta function.
No, the whole model is actually spin model or fermion.
Yeah, you can represent it in spin language. So how does it help?
Well, 1D is solvable by beta and Zas for starters.
Well, it's not.
Hardcore bosons.
It's
of course,
not.
are solvable.
It's
They
not.
are-
When there is
these are
nearest
hardcore.
neighbor interaction, it's not solvable by beta. It's seemingly simple, but it is not. I'll talk with you. I'll show you.
It's representation.
You said the interaction is only between layers, but you have
No. Interaction between nearest neighbor particles repulsion and attraction
Okay.
between layers. Sure, and there are angles where
Okay.
repulsion changes by
Okay.
attraction.
Because you said only attraction between layers.
Oh, no. I'm saying that in principle it's possible to have attraction between different layers. That there is always repulsion within the same layer. Okay, so now we're talking about single chain. And the problem was solved by continuous time path integral Monte Carlo, so-called worm algorithm, invented by Nikolai Prokofiev and Boris Svistonov and adopted for continuous time. Yes, together with Panisenge, and so Barbara actually developed the algorithm for layered systems, and there was some modification to take into account pairing, so she did really great job. So yeah. Okay, so what are the expectations? So let's say, again, cartoon. We have one particle per layer, and one possibility, they are independent from each other. They just move around and feel, let's say, weak potential. So these are called independent layers. Another option is that there is a strong correlation, but correlation which can be represented by flexible string.
This is chain in real space or in
Real space. Real space. Actually, if you're talking about quantum space, you have to add another coordinate that will be nimbrane.
Okay.
So the second possibility, single rough chain. And third possibility is that this chain is stiff. So this is the expectation. Okay, so how to see this? In order, first of all, let me give you some idea that the possibility of formation of rough chain is not obvious at all. Because on one hand, you need for just one particle per layer, you need tunneling to be smaller than typical interaction energy to have formation of pair. Well, you can argue that for delta function potential there is no lower bound, but for dipole interaction there is, and in fact if you consider, let's say, dilute gas of chains, there is always lower bound. So a good fair estimate is that typical tunneling must be comparable or smaller than interaction energy to have chain formation. Okay, so now on the other hand, what is the condition for forming rough chain? Let's presume this chain is formed, and we can describe it by sort of string behavior. So this is the displacement, let's say, for the cigars, displacement in each layer. X is now variable measured along the layers, and Y is how this string is bent and deforms. This is the point. And there is a potential, optical potential, which provides a sign Gordon potential, and we know what to expect from this system. if this coefficient is Lattinger parameter essentially is less than 1/2, the chain will be stiff. Chain will be stiff. So sign-Gordon potential is strongly relevant, and you have just non-fluctuating essentially chain in the limit of large number of layers. You can relate speed. Actually, this Lattinger parameter is expressed in terms of typical speed of sound along the chain, and by slightly deforming the chain and relating it to typical energy of dipole-dipole interaction, you can express actually speed of sound in terms of the dipole moment. And then, if you combine it with the effective mass definition, all things in the definition of Lattinger parameter, you'll come up with this relation between Lattinger parameter and typical tunneling rate, typical interaction energy, and distance between layers versus distance between sides in the lattice. Now you see that on one hand you require that, on the other hand you require this bigger than 1/2, and furthermore, in order to have really quantum system, you require that temperature should be low enough, so that, let's say, it's below the typical sound excitation along the chain. Okay, and then you can expect that you're essentially below the Dzerzhinsky-Kosaris-Towers transition at zero temperature. Okay, so summarizing these conditions, you see that on one hand this must be true, on the other hand this must be true. But you can say, okay, let's make By much smaller than Bz. Okay, but then immediately you increase J. So in fact there is no small parameter, and you're essentially working in the regime of everything of the order of 1. It's absolutely not clear that you can have rough chain. Okay? Quantum rough. Not thermally rough, quantum rough. Okay. So what is measured? We measured gyration radius. What it means? Let's say we considered fixed number of layers and pinned just one particle at the top. It was not moving. The rest of the particles was free to move along the planes or cigars, and we determined the average of this quantity, imaginary target, where R is the displacement of particle in each layer with respect to the center at half distance. If particles are independent, then this gyration radius will be scaled as size of the system. Essentially, we will see kind of equal probability to have, if you do, let's say, columnar map, you will see equal probability to have particles everywhere. However, if a chain is rough,
but they divided by the number of layers they have.
yeah, with some, yeah, the one number of layers and some.
But then, if you divide, it can be proportional to a square.
No, it's square. Square.
Is it defined modular lattice constant in some sense?
Yeah, it's all discrete lattices. It's lattice.
No, what I'm just asking, for instance, you have this pinned atom on the top, and then in the next layer, so the particle can shift, one lattice constant to the left. So then, should you consider this old particle or the new particle, which is right below? So
No, it's just it's okay. It's not grand canonical calculation. We always have one particle per layer. Particles do not vanish. Particles are not created.
So it's single particle problem.
It's a
within
single
layer?
particle per layer, but it's n particles in each layer. I mean, n particles total, one particle per layer. We have exactly n layer particles.
So you have single particle problem within the layer, and there is no tunneling between the layers.
No tunneling between layers. But particles interacting. This particle interacts with that.
So you are just measuring if the other particles are free to move when you fix one. That's what
Yeah, we fix just one particle, and the rest are free to move.
Yeah, and
As
you
long
see
as
how much they
energy is
move
free.
away from that point. Basically.
Yeah, they can move away.
I see. This n particle Schrödinger equation, basically.
Yes.
And the statistics just doesn't matter, actually, right? Because they cannot take phases.
Doesn't. Yes, absolutely. Statistic doesn't. For multi-chain it does, but for single chain it doesn't. Okay, and so in the case of rough chain, we expect logarithmical dependence, and when polymer becomes stiff, it should be of the order of 1. This is the expectation. Okay, so this is the result for cigars. Well, I should have added plus n layers, so the actual dimension is 1 plus 1 plus n layers. So in this, yeah.
In usual in 2D at finite temperature, Castro-Starless transition, the argumentation is that it is transition, it is play between the entropy and the energy. Can you give us a sort of an interpretation for zero temperature?
Yes, in one dimension it's essentially, you can consider some effective quantum temperature. Basically, transition is driven by quantum fluctuations. You can say it this way. Let's say in sine-Gordon you have two possibilities. You have the possibility to excite pairs of kings. They carry some energy. And phonons. If energy of kings somehow becomes smaller than phonons, essentially sine-Gordon becomes irrelevant. And otherwise, if bigger, then it's relevant. And you'll see that it's exactly the condition for, and you know what zero-point fluctuations are. So you can calculate, you compare energies, and you see that exactly at Latinger parameter 1/2, you have a transition. The nature of the transition, to quantify it in terms of Brzezinski-Kosterlitz-Stauss transition, you have to really consider the mechanism of formation, which is instantons. And formally, it's exactly the same as vortices at finite temperatures. Exactly the same. Yeah. So in 1 plus 1, we have the following graph for duration radius. It's a function of interaction between layers. What we see is that for small interaction, essentially this is kind of size of the system 50, so this is mean square, which exactly corresponds to averaging over length of 50 calculating, right? So these are independent layers. Then we have sort of more or less independent layers still, and then they curves diverge. Right, so expectation is that in this, well, evidence is that in this region we have rough polymer, and eventually for strong interaction, duration radius becomes of the order of 2 units. Okay. In 2 plus 1, the region is narrower, but still exists. So the curve is qualitatively similar. Yes, and now I'm going to demonstrate how, let's say somewhere here, how duration radius depends on the number of layers. Right? So we have simulations for different number of layers. So now I do this cut, and
It does mean exact.
oh, exact. It's kind of. It means if interaction is 0, you can do averaging exactly. Trivial.
Only 1 point there.
Yeah, just 1 point.
So which size is bigger, the total thickness of the stack or the
Okay,
width of
let's
the
see.
cigar?
Now you have 36 by 36. Here, maximum you have 10 layers. So stack is
Actually, it's
10 layers. Yeah. It's, oh, you mean distance?
yeah.
No, calculations were done for equal distance between stacks and the lattice, square lattice.
Right. So then if it's kind of a thin stack, you can take one of the particles and move it away, so it exceeds the critical angle at which the dipole interaction becomes repulsive.
Right.
So you can always ionize, well, sort of kind of dissociate this.
This is probably the mechanism which tells you that there should be a threshold for interaction. If you had delta function
No,
interaction,
for dipole interaction. For the dipole.
but dipole, yes.
Yeah.
So only this process is not really relevant only when there is a when V over J exceeded some threshold. What we see here is obviously there is a room. You have chains which are formed and simultaneously they are up. So still kind
There's a
of
probability that I can take
Yes.
one atom and
absolutely.
move
Yes.
it away
This-
and it'll become repulsive, so it just goes away.
But the probability obviously is not really dominant. It creates some sort of virtual cloud, but there is a finite binding energy. So you cannot, at finite temperature, of course, you can ionize it, but at zero temperature, there is a range where chain is stable.
So what is the classical ground state of these particles? Is it just a straight? Do they want to be as close as possible to each other?
Well, if you take classical at zero temperature, I believe it will be just straight.
So can I think about then if I have an infinite system, basically a very large system, so somewhere in the middle of this string, so basically I have a local potential that a single particle feels, and this uncertainty would be simply, quantum motion of a
You
single
can
particle.
say that, but the point is I'm going to show you that the dependence is actually logarithmical. So if it were just simple uncertainty, it wouldn't depend on the number of layers, naively, right? But now it does depend on the number of layers and pretty much logarithmically. So it's quite consistent with the idea that chain is quantum rough, logarithmically divergent fluctuations. One end with respect to the
But if you just consider harmonic interactions, forget about cosine, it's like Latinger liquid, you always expect power laws, right? That's what you're talking about.
No, I'm considering mean square formation
understand.
of the, yeah.
But this increases logarithmically if you
Yes.
consider just Latinger model.
Yeah, yes, exactly. Yes, it means that for these chains, sine Gordon is irrelevant.
Yeah, okay.
Okay? So this is what it means. Yes, Latinger liquid the same. Yeah. And
Do you
essentially,
think that at the infinite body it will be real phase transitions from the left on the right?
you mean from rough to,
Yes.
yeah, it's supposed to reach downwards. It should be
In
both.
1 plus 1 plus
Yes.
1?
In 1 plus 1, yes. Oh, you mean in 2 plus 1?
Yes.
Oh, in 2 plus 1, we believe the transition is still post-Strelitz-Taulis because the effective dimensionality is determined by the structure of single chain. It really doesn't matter if it's really
Is it thermodynamic limit?
Yes, we believe so. But it will be two-component post-Strelitz-Taulis, which is different from one component, but still it's essentially post-Strelitz-Taulis.
In both transitions, on the left and the right?
Oh, you
Show
mean-
the previous one.
Oh, you mean,
This one,
you mean on this side?
yes.
Oh, I don't think that there is no transition, it's a
I see.
crossover. It's a crossover.
Yes, of course.
It's a crossover just
And
for
on the right it will be
It's a
something
Kosterlitz
like
law.
Kosterlitz.
Kosterlitz. Well, in the soup of polymers, there could be transition in here as well, but not for a single. Okay, effect of temperature. Okay, here what different curves are. This is essentially cutoff one. It means that we ignore we consider interaction when particles just exactly on top of each other. This is essentially delta function interaction. And this is what I was thinking that it's possible to solve by beta ansatz, but it turns out to be not. And apparently for cutoff 1, there should be no threshold delta functions. But for cutoffs, higher cutoffs, when there is interplay between attraction and repulsion, there is threshold. And what we see is essentially that increasing the cutoff does change the behavior, but it remains essentially with good accuracy permitted by error bars logarithmical. Effect of temperature. So simulations were conducted for different betas, right? And what we see is that there is some shift, but tendency more or less remains the same. So we believe that we are well in the regime of quantum behavior, not classical, not thermal.
So you're saying it's still logarithmic displacement?
Yeah, logarithmic behavior. So temperature here is is not relevant much. It's still, we believe, in the regime of zero temperature, right? Because
So
if
actually
it
you
were
expect
thermal
it should be
dephasing, it
linear.
would be shooting up.
Yeah, it
Thermal-
should be linear, right?
Yeah, it will be shooting up, so it's definitely, behavior doesn't change. So temperature plays a role of some parameter, not really significant. Okay, now let me discuss soup of flexible chains. So what would happen if we have many chains and what the possible states are. So one expectation is that there is a possibility of forming superfluid of these chains. What it actually means. Superfluid of chain means that if you measure expectation value, let's say order parameter in each layer, now we have many particles in each layer, it is zero. So no superfluid in each layer, but if you take product of all operators across the layers, you expect this value to be non-zero. So this would be an atomic chain superfluid, and if this is not zero, then it would be n-component superfluid. So this is
permit algebraic decreasing of the coordinator, or you would like?
yeah, yeah, sure. Okay. So basically we address the question. Now we have many chains, they can interact, can switch with respect to each other. And so what is the nature of, what are quantum phases of such
Now,
things?
when you have two chains,
I'll show you the
no,
solution
one
for
second,
two chains.
she's another question. How you decide, you see, when there are two chains close to each other, that one particle belongs to this chain, not to the other chain?
Well,
So what's the physical criteria?
we don't decide on that, algorithm does it. Basically, algorithm,
No, I understand the computer will decide that, but what's in the physical there? Because I don't see a reason, you see. I see this link, it's simply in your mind, it's not physical.
well, basically, okay. So we
You
don't
see,
put
like you have, you
chains.
see the two crossing there. You might think that they are two crossing or not crossing. You see, it's equally valid.
Yes, so with
so
equal
which-
probability, with equal probability.
So what's the
You
point of
offer-
having two chains there? You see, I don't understand. You see, how you decided there are two chains, really?
Well,
But you promised to give the definition of chain, so that...
so for single chain we can.
Yeah,
but
but
that's
in
in-
this
mind,
case
you see,
no,
also...
no, no,
it's
no,
not
no, no.
physical.
For single chain we can do.
No, one chain I understand, but
Yeah.
two of them I don't.
Yeah, it's okay.
Okay.
How you decide two
Okay,
chains? You see?
so
How
I
you
can
decide
give-
that this belongs to this part,
No, no,
this
no,
chain
no.
or that chain?
No, no, Ariel. The definition. Of course, we are not. We all goes in terms of order parameter. Definition goes in terms of order parameter. I gave you a definition of.
Okay, I have one cigar here.
This is the definition of the chain.
No,
Take it
that's
as a
right.
definition.
I have, you see, one cigar here, and I have one particle here, one particle
Right.
here. How I decided this one belongs to this chain and not to the other chain? How you decided this particle belongs to one or the other
I don't
chain?
need to decide that. I introduce order parameter and claim that there is possibility of this phase and not this phase. This what I.
You said that the particle number is conserved in each cigar. That average says
No,
that
no,
that's
no,
not true.
no. Of course not. This is a standard. If now it's grand canonical. For single chain, yes, but for many chains.
So now you don't conserve the particle number.
Yeah, no. But these calculations are done in grand canonical.
So if this is a lattice model, you can easily define a chain. You can
Well, you
first
see,
you
no,
get
no,
two-leg
I-
ladder, three-leg
no,
ladder.
yeah,
four-leg
but you
ladder.
see, it feels like it's a mathematical game. You see, it's not physics.
No, we don't need to talk about chains now when there is a soup. You look on the order.
I don't know
parameter.
how he's going to change the particle number in a cigar. How he's going to do that?
This is grand canonical.
No, I understand what it's
calculation.
in your mind, you see, but I don't know how you're going to do this physically in an experiment.
But it,
Oh, it's
That's
another
it.
matter.
No,
It's another matter.
Look,
If you believe
how-
that grand
how you-
canonical describes superfluidity correctly, then we are on the same. If you don't, then what can I do?
No. I think you're pushing it.
So this is now definition of the chain order parameter, chain superfluid, when this multiplicative order, and okay, it's in my mind that I view it as a kind of entangled superfluid of molecules. For two molecules, for two layers, it would be called paired superfluid. For three layers, it would be triple superfluid, and so on and so on. Okay?
I guess there is a standard way. You just take couple it, multiply by the same with daggers, would take position I plus j, send j to infinity. So
Oh
I don't
no,
think this is
no. Of course, it could be reformulated in terms
Right.
of density matrix. Here it's single density matrix. Here it's an n density matrix. Yes,
there is no.
of course, it's a standard thing. I don't think we should argue about that. Or if you wish, it's you can define in terms of spontaneous breaking of symmetry in terms of Bogolyubov, and so it doesn't.
Can I ask a question? You define it by taking the same I here in the
Yeah.
order parameter,
Yeah.
it's the same I.
Yes.
Why can I not let the I vary plus minus 1 or something equally well? I mean,
Yes,
that
yes,
is sort of
yes,
related.
It's an
You can-
arbitrary number.
You can do this, but the point is that if you take, for example, one operator and take it away very far,
Yeah, if you take it far
It
away,
will
but
be
I mean,
zero.
if you take a little bit, it shouldn't make
a little
any
bit it
difference.
should matter, but if you take it far, it will be zero. It will be zero. So basically, the only correlator which is not zero is when all x within the same layer are close to each other, and then second x is somewhere, but all must be bunched together. If you take just single particle away from that, it will be zero.
You just-
like average over the duration radius or something, that's probably where they are
Oh,
not zero,
no,
yes, or
no,
something.
no. For superfluid, you will not see anything, because you have to basically switch word lines, and it will be.
But ask you just argued for a single chain. It's fair to expect logarithmic increase of the distance. So it actually means that in this space, I expect that this will go
Yes.
down as 1 over log
Yes,
squared.
yes. Logarithmically, yes.
So it actually means that it's non-zero if you consider as a non-thermodynamic limit, m is finite, you allow it to decay as some small power
Yes,
of m
yes.
log of m.
Actually,
is
what
still
it means
superfluid.
that the actual size of the globe is logarithmical with the size of the layers.
Yes.
Yes. Okay. So I'll show you this. Okay. Yeah, and the essential thing is that this should be viewed not as word lines, but as a membrane. So basically, it's different universality class. If we're talking about phase transitions, these are membranes, and it's not clear really how to treat this system.
Is it do they have elastic energy associated with the, because you drew them?
Well, yeah, I'll show you some formulation of some model which does include elastic energy, but in a kind of direct simulations, it's hard really to extract elastic energy. But definitely sound, which can propagate, it's a measure of elastic energy. Yes. There is a sound wave. But once chains are formed, there is a sound wave. I'll show you. Okay. So first step is just model simulations, J-current model with delta interlayer interaction, simplest one. So no long range, just to understand what's going on and how to measure things.
What's delta interlayer? Delta means the same
Delta
place.
function. Yeah,
Yeah, but
it means
it couldn't.
It
It's
means-
intralayer, not interlayer. then.
no interlayer.
But then it's not a delta function. It's separated by the layer.
Yeah, but it's delta function along the layer. It's delta function along the layer. It's like that. One layer, another layer. This is x. One particle here, a particle here. You have delta function.
Oh, okay.
X1, 2. So the first term is a standard dual formulation of just one layer Latinger liquid. J here are integer currents living on space-time lattice. Second term is interlayer interaction. And the third term is chemical potential, which can vary number of particles. What is measured? Yes, and these currents are satisfying Kirchhoff rule. It's a standard formulation of XY model, oriented loops. These W's are winding numbers. So essentially total current along space and along time. And the measure of superfluid stiffness and compressibility are fluctuations of winding numbers, right? So once these fluctuations are not zero, we should expect superfluid stiffness. And if we have independent layer and there is no tunneling between layers, then it's natural to expect when you take winding numbers correlator between different layers, it must be zero, or maybe some weak quantity. However, if there is chain formation, then we would expect completely different picture. We would expect that winding numbers equally, let's say, basically the probability to have current in the same direction is high, but any current in the opposite direction is essentially zero. So we perform sort of Fourier transform along the layers. Q runs along the layers. No, perpendicular to the layers, and calculate Fourier component of these winding numbers. So in terms of the Fourier component, chains would correspond to the following state: when total winding number is not zero, but any harmonic of winding numbers different from zero will be zero. This is what we got. Basically now it's back to real space. So the Z is a coordinate of the layer. So correlator between different layers. So we took periodic boundary conditions along perpendicular to the layers. It's convenient just to do the Fourier in this case. Okay, so if interaction between layers is weak, the result doesn't really depend much on the size of the layers, right? So we have 12 layers. We have a size 24 by 24 and 48 by 48. And two curves essentially overlap with each other. It means that if you are within the same layer, correlator is large. If you go to next layer, correlator falls down. Essentially there is exponential decay between layers. There is some drag effect between layers, but it's weak. If you now go to higher values of interaction, you see slightly higher values of interaction. For small size, you still seemingly have sort of exponential decay of the correlator. However, once you switch to bigger size, look, parameters are the same. Correlator becomes essentially flat. It means that in Fourier space you got delta function. So we interpret it as a formation of superfluid of chains. Yeah. And behavior is similar for 1 plus 1 and 2 plus 1.
So the density, the chemical potential.
Oh, these calculations for integer filling per site. So this is essentially zero chemical potential. The question with chemical potential is interesting. It's more complex. Okay, so there is some evidence from 1 plus 1 bosonization. So actually this problem was sort of considered by many people in terms of sliding phases. And the bosonization scheme was first applied by Vishnawat and Carpenter to this system. But somehow this molecular phase was not discussed. And actually later, Ludwig Matthew, who will be here, I believe, right?
He couldn't come, just he informed there.
Okay. So he considered the problem of just two layers. So basically what we do here, we just expand Matthew's scheme and marry it with Vishnawat and Carpenter, and just there is a very little contribution for this. So basically if you consider this system with backscattering effect, so this is standard ansatz for Latinger liquid within each layer. There is now forward scattering interaction and backscattering interaction. We ask a question when this term becomes relevant. It means formation of the chain. And when it becomes relevant, essentially when the Latinger parameter defined in this way becomes, well, it's essentially the same as a formation of a paired state for two chains. So it doesn't really depend, practicality doesn't really depend on the number of layers.
So to get these terms, do you need interactions within each, I don't know, cigar or whatever to call it?
Well, it's not written here, but in principle, of course, it's present.
So if you were to write just, I don't know, both gas there with no interactions whatsoever, and I mean, in each, I don't know, cigar. So,
Ideal gas, yes.
yeah, so and then couple them the way you want to couple
Well,
them. Isn't
ideal
that-
gas, it's a problem. I cannot really write Latinger liquid.
Yeah,
There should
it-
be some speed of sound, right?
but you still can couple the you know the cigars with each other.
Yeah, it's extreme situations, sort of.
Is it exactly solvable model?
Oh, well, I don't know. I don't know. I don't know. You mean in terms of bosonization?
Well, in terms of just calculating, I don't know, partition function, I think it's just it must be
we
exactly
didn't look.
solvable.
We didn't look on that. Would be interesting. We didn't look on that. Okay. Okay, so basically, to get the flavor of what will be happening. So let's say this term is relevant. Then we can expand cosine and leave only these terms. And what it gives, it essentially gives a sound wave along the direction, right? So there is a gap dependent on QZ, which vanishes when QZ is exactly 0. What it means, zero gap for QZ equals 0, it means you can translate the whole chain as a whole, right? But all other excitations are gapped, which means propagation of sound along the chain direction, which is consistent with the kind of perception that sound can propagate along a single chain. Okay. And we identify this transition with the formation of this order parameter. Okay. To get better insight what is really happening with the chain, what is the superfluid, in fact, it's pretty simple object. It's a condensation of center of mass of molecules, nothing else. Nothing else. It means that all this flexing doesn't really matter. What matters is just dynamics of center of mass. Okay, so how to see this? Well, each individual phase, it's a dual phase to actual superfluid phase, can be represented as a sort of common phase which is attributed to the center of mass of motion, and fluctuations around that. Obviously, gapped state means that these fluctuations at finite momenta can be ignored. And if you use this ansatz and put back into the action, you will get factor of n in here, and factor of n in the cosine. What it actually means, it means that now the Latinger parameter for single chain is going down as a number of chains. It means you just get heavy chain, and in order to keep it superfluid, it's really you have to stay for finite n. So in the limit of infinite n, it will be localized anyway.
Do you get sliding Latinger liquid phase here?
Okay.
Because that's what
Yes.
Kane and
Yes.
Usher
Well, okay. The Latinger, sliding Latinger phase. We don't believe it exists. Oh, okay. We don't believe we describe exactly the Latinger sliding Latinger liquid phase, because sliding phase presumes that there is standard order retained within each layer, but Josephson tunneling becomes irrelevant. This is the assumption. In our case, order in each layer vanishes, doesn't exist. But order, the only order which can exist is for the total phase.
So you basically
center-
never see this phase in actual numerical experiment.
No. No. We believe this phase intervenes, happens before the actual sliding phase. It was not considered by sliding phase analysis. So somehow it was ignored. Okay. So now the question is what happens at non-integer filling. Well, the non-integer filling, you see, formally speaking, this term is not integer, and cosine term is washed out, so you would expect that superfluid always exists once you deviate from integer. But in fact, it's not that simple.
What it means physically?
Okay.
What is the model of this?
What it means
For a real system.
for real system, it means the following: that let's say if you prepared for each layer, let's say with integer filling, one particle per site, let's say, and you increased the interaction, you form this condensate. If you start increasing number of layers, you will always get in the mode insulator phase.
I see.
So
After you will have more.
yeah, it will be always mode insulator phase. But the question is now, let's say you are far from integer filling, let's say half filling, or 1/3. Will you still have superfluid, maybe weak superfluid, with small superfluid stiffness, but still superfluid forming? Okay. Well, at least on the level of the same bosonization analysis, we know that if you put by hands, let's say, higher order operators, higher density operators, let's say not just lowest order, let's say density, but density to the power of n interaction, then you generate backscattering term, which makes deviations from integer filling irrelevant, provided this product is integer. So in this simple thinking, for this is the average filling, this is number of layers. If this satisfies this condition, external period, any arbitrary small external periodic potential will localize the superfluid. But there is more to that. In fact, we believe the limit of n going to infinity, filling becomes irrelevant, essentially. I'll give you some reason for that. Oh, this is the simulations for 2 plus 1. For 2 plus 1, it's quite amazing. If you increase interaction, let's say for small interaction, you have superfluid of chains, and changing chemical potential doesn't change much. Now you go to the limit of strong interaction of chains, and what you see that there is let's say that at 0, oh, okay, it should be half filling. Okay, it's not exactly 0. Okay, model was reformulated to have 0 chemical potential at half filling. Okay, I didn't mention that, but it's really shift. Okay, doesn't matter. So you see some sort of checkerboard order formation at half filling, which sounds reasonable. You see gap formation, so essentially number of particles doesn't fill the gap within certain limits. But if you measure then how this checkerboard order parameter depends on the size of the system, you will see quite amazing things. So this is for superfluid. There is some residual order parameter which exponentially decays with the size, and so does the insulating state. So the question is, what is the order there? So it's still...
Can you possibly detect a liquid phase if it were there?
Yes, this is liquid phase, by windings. We detect by windings. This is clearly for small interaction. Okay, this is 0.5. It's pure superfluid, perfect superfluid for 4 layers. We see it's superfluid. Once we increase the interaction...
No, I mean neither superfluid nor an insulator, just a liquid, like Fermi liquid, I don't know, couple 2 Fermi liquids by weak repulsion. Is there going to be a Fermi liquid?
Definitely it's a gapped state, but what is its nature, still not clear. What kind of order existing? Maybe it's quantum disordered state. We don't know. We don't know. We looked for valence bond order, we looked for checkerboard order, or higher harmonics. Nothing. Everything decays like that. Okay, now let me give you an argument why filling factor is irrelevant. And a very simple example. Let's say you have just two chains in 1 plus 1, and let's you put it on a cylinder. So these two chains can move on a cylinder, and this is we consider them distinguishable for sake of argument. So there is no switching between red and blue. And this is the interaction between chains. It could be either attractive or repulsive. In order to sort of restore the periodicity, this is replaced by a cosine term where r is the radius of the cylinder. By the logic of relevant renormalization group, we have to consider what happens to the first term of this expansion. Other terms will be higher harmonics. And it's clear that now the role of the Lattinger parameter is played by this factor, which has r squared. It means if you take large enough cylinder, you will always be in insulating state. What it means is that if you have attractive chain, they will be at top of each other, so essentially difference will be zero. If you have repulsive chain, they will be at the opposite ends. Repulsive chain would correspond to introducing pi into cosine, and it will goes to here. So this reasoning tells us it doesn't really matter what the filling factor is, provided chains are long enough, so you can use logic of renormalization group. There will be bound state, either together or on the opposite sides. What happens with many chains? Yeah. So localized states at arbitrarily small density for two chains. But this is not a proof. This is just argument that the same should happen for many chains. Okay, so in the case of many strings, you can reformulate problem in terms of many colored strings and do some simulations, which we did. And in 2 plus 1, let's say we can confine strings into some potential, effective potential. So psi now in 2 plus 1 would be a combination of y and z displacement. It's not original psi operator. And actually you can do the same ansatz instead of the cosine. Result doesn't change much. Okay? And if you perform simulation of this and this model for attractive chain, we see collapse of chains together for arbitrary small interaction, which is consistent with the logic that effective density is effective size of the system determines the threshold for Lattinger parameter. What happens for repulsive chains? We don't know, but we expect that consistent at least with the two-chain result, it also will be some sort of bound state. Okay, I think I'm done. Oh yeah. Let me give you another qualitative argument why filling factor doesn't matter. So we call it caging effect. So let's imagine you have strings, and apparently there is certain filling factor, but they fluctuate. They fluctuate and form some sort of cages with respect to each other, and so you can view it as a thick molecules with the size always fitting the space between them, so if chain is long enough. And in this sense, you always at integer field. Okay, I think I'm done. So basically, what we discussed. First of all, I demonstrated that there is a formation of single chain ab initio simulations. So there is a transition into auto-localized state. Okay, Then we also observed superfluidity of flexible chains in model J-current type simulations, not ab initio. Then we conjectured that in the limit of large number of layers, filling becomes irrelevant. So no chain superfluid. But the question remains, what is the nature of this state? If not superfluid, it's insulating. What is the order? This is open questions. The possibility is that it's Wigner type solid of rough chains, okay, or maybe quantum disordered state.
Do you think that this state can exist?
Quantum disorder? Well, why not? Is any theorem that
Oh, yes, there is no theorem, but is it possible to formulate its property on some reasonable language?
Well,
To give definition something.
well, its definition would be that there is no order. Well,
Correlation functions decay algebraically.
well, it could be
Critical
gapped. It could be gapped state also, but without any order. But but I really cannot answer this question. But at least I'm giving you the flavor of what we see in simulations.
You can see something.
Yeah, we see the kind of would-be checkerboard order which decays exponentially with the size of the system. So,
The sort of quasi-crystals.
maybe, I don't know. It's open question.